These are the notes for Thursday, and we're beginning our look at what we call Taylor and Maclaurin series, which are types of what we call power series, which we'll get to later. We're first going to talk about Taylor polynomials. And the goal of this is, I'm going to go to my calculator here, and I'm just going to leave that. We're going to look at some functions like sine and ln x and e to the x and cosine x and a few other functions that we are going to eventually write polynomials that hug those functions so closely that they give the exact same values, because polynomials are the easiest functions to work with in any form of math. They're the easiest to take the derivatives of, to integrate, to find the zeros of, the maxes, the mins. All that good stuff is really easy when you have a polynomial function. So we're going to start with the sine wave. And we're just going to go put a sketch of the sine wave on here. Sine of 0 is 0. Sine of pi halves is at 1. Sine pi, etc. We're very adept at knowing what a sine wave looks like. And in Calc 1, we talked about tangent line approximations. A line tangent to the curve at a given point of tangency. And on this one, we're going to look at where x is 0. Well, when x is 0, y is sine of 0, or it goes through the point 0, 0, which I can already see on my picture. And in Calc 1, we talked about tangent line approximations and how we can use this line of tangency to find the values on the curve as long as we stay close to the point of tangency. But as we start to veer away, we get farther and farther away with our tangent line. But in the proximity of the point of tangency, the tangent line's a pretty good approximation. So recall from Calc 1, we would then go get the equation of the tangent line. We would need a point, and we would need the slope. And the slope is the derivative, so f prime of x is cosine x, and f prime of 0 is cosine 0 or 1. And we would say that that line is the line y minus the y I know is equal to the slope there times x minus the x I know. Equivalently, y is equal to 0 plus 1 times x minus 0. And you might ask, why is she writing it like that in that weird form? That's just y equals x. And it's because this weird form right here is actually what we call a first degree Taylor polynomial, which will make sense when we get to the second page. But like I said, that tangent line approximation is only good when I stay really close to the curve. So as long as I'm close to the curve, I can estimate the sine of point 2. The sine of point 2 would equal, and again, sine of x, they're equal, so it equal 0.2. And if you were to go to your graphing calculator, it wouldn't equal it. Again, this is a tangent line approximation. Sorry about that. So if I were to go to my calculator and do sine 0.2, the actual value on my calculator is 0.198669338. And my approximation is pretty darn close. Keep in mind, it's only close because I stayed close to the point of tangency. Also, it's a little bit of an overestimate because my tangent line lives above the curve, also known as the curve is concave down over there. So what we're going to do now is talk about, could we do better? And we did one method of doing better earlier in the year. We did Euler's method, where we said, well, okay, yeah, that tangent line's not so good, so let's adjust it in little step increments as we travel around the curve. And that was better. Euler's method was good. But we want to be able to handle that curvature and really try to hug that curve. Because if you look at, again, here's your sine graph. If you were even just to look at that graph like right in this area, boy, you know, I would be really good getting an approximation in that whole region if I could fit a cubic to it. That looks very cubic-y. Well, if I could go like this, that looks very quartic. And if I could just keep fitting a polynomial to the curve, I would increase my range of accuracy so I'm not so tied into being close to that point of tangency. And is it even possible that I could get a polynomial that's spot on the same? And the answer to that is sometimes. So first thing we're going to do is go do a little exploring on our calculator. So if you could take your calculator, and we're going to set our window from -9 to 9 by 1s, -4 to 4 by 1s. you can pause the video and go do that. Then we're going to go graph in y1 the actual sine wave. In y2, I'm going to graph this polynomial. Now in class I graphed it by increments. I did x first and it just made a line. Then I did this x cubed minus divided by 6 tacked on here, and it made a cubic that hugged the curve. And then we tacked this one. But for time purposes on the video, I'm just going to do this all in one. But keep in mind, as I kept adding another term to that polynomial, I just added another curve to my graph. So take a look at what this looks like. The sine wave was in blue and my y2 is in red, and you'll notice that's really a good fit. Well, how could I make that fit it better? Well, how about if I continue that same pattern and up the degree of, by the way, if you go look at this, my first degree polynomial would just be y equals x, and that's what we got on the previous page. That was our linear approximation, but right now we are upping the ante and trying to fit a polynomial to it. And you're going to ask, where does this polynomial come from? Where'd she pull that from? That's our task on the next page. I first just want you to see how these polynomials are really fitting that curve nicely. So I'm going to add x to the 9th divided by 9 factorial onto that curve, and now watch it graph it. So there's my sine wave coming along. And then in red, that is my polynomial that I modified. I added an x to the 9th over 9 factorial on there. And notice it came in, hit right about here, and then it really hugged the curve very well. It hugged it, and then it kind of veered off on the end. And you can guess, well, if I did the next term and added that on, it'd be even and better and better. And if I did it on out to infinity, it fits the curve exactly, and that's our goal eventually. So where did that come from? We have a mathematical historian named Brooke Taylor who came up with what we call the Taylor polynomial approximation method. And he said that he can find, as long as the function has n derivatives, what that means is you can keep deriving it over and over again. It means basically we have no discontinuities or cusps, asymptotes, vertical tangents, that good stuff. But as long as we have a function where we can continue to take the derivatives over and over, like cosine x, ln x, e to the x, all those functions, we can write a polynomial that approximates the function. Let me take this language apart. This would be called the nth degree polynomial approximation. And we start by just doing the function value at c, which is the center. On mine, my c right here is the origin on the sine one. So that would have been f of 0 plus f prime of 0 times x minus 0. Notice that's my tangent line approximation right to there. But then what I keep doing is I do the second derivative at 0 over 2 factorial, and then x minus c squared, etc. Now mine was centered at 0, and when it's centered at 0, it's called a Maclaurin polynomial. So every Maclaurin polynomial is a Taylor polynomial. Every Taylor polynomial is not a Maclaurin. Maclaurin has to be centered at 0. Taylor polynomials, we can offset them a little bit. So for a Taylor polynomial, we can center it maybe at 3, or I don't know why it won't allow me to write on that, but it won't allow me to write on my graphing calculator. So how do we go about getting that? And I will do that for you right now. We're going to do the one for sine, and then the other one we do in your notes. So I'm going to show you where that sine one that we just did on the previous page came from. It starts like this. First of all, note what degree. I'm going to do a 5th degree, so I'm going to take that out till I get x to the 5th. My function is f of x equals sine of x, and I would write that off to the side. I'm going to do a 5th degree polynomial to approximate that. F of x equals sine of x, which I'm going to approximate with a 5th degree polynomial. I'm going to center it at 0. How do I know that? Because it said Maclaurin. Maclaurin implies that your center is 0. And I'm going to use that to approximate the sine of 0.1. I'm going to then find my error, etc. First thing I'm going to do though is write this out, because the more you write it out, the better you memorize it. So you do f of c, in our case is 0, plus f prime of c times x to the first over 1 factorial, plus f double prime of c times x to the second over 2 factorial, plus f triple prime at c, x cubed over 3 factorial, plus, and then I'd have to do the fourth and the fifth, and I can't fit them on there, but you get the general gist. So what I need to supply to this model is all these numerical parts of the coefficient, because I've got the factorials on the bottom, so really it involves just taking a bunch of derivatives. I know that f of x equals sine x, so f of 0 is sine 0, which equals 0. So that's going to become a 0. F prime of x is the derivative of sine, which is cosine. F prime of 0 is cosine 0, or 1. So we're going to replace that with a 1. F double prime of x, the derivative of cosine, is negative sine. In particular, at my center, it's going to be 0. And then F triple is the derivative of negative sine x. And remember our little sine, cosine, negative cosine, sine. So my derivative of negative sine is negative cosine x. I'm going to be doing that at 0. Negative cosine 0 is negative 1. I'll do one more. The fourth derivative, the derivative of negative cosine is sine. And at 0, phew, it's kind of labor intensive, but it's kind of mindless labor right now. I'm just taking some easy derivatives. All right, and then I would do the fifth one as well. So you can kind of see the pattern. What I've got for my polynomial expansion is 0 plus 1x plus 0, because all this is going to go to the 0. And in front of the third derivative is a minus 1. The fourth derivative is 0 again. And if I'd done the fifth one, you can kind of look, if I'd done the fifth, the derivative of sine is cosine. At 0, it's going to be 1 again. So that's going to be a 1. For the fifth, it's going to be a 1x to the fifth over 5 factorial. I'm now going to clean this up. That gives me x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And you can see the pattern. Had I been asked to do a 7th degree one, I would be pretty certain that that would then go mine. All the even powers seem to be wiping out because these derivatives are 0. And the odd ones seem to be alternating signs, but the powers match the factorial on the bottom. This is called the 5th degree Maclaurin polynomial for sine of x centered at 0. Well, it said to use this to approximate sine of 0.1. So sine of 0.1 can be approximated by putting a 0.1 into this polynomial. And when I do that on a calculator, let's go do that off on the side here. Let's go to a working window. I end up getting, when I do that, actually I wonder, I'm going to see if this is still up there from last hour, see if it'll, no, won't do it. Okay, so I do 0.1, and then I do minus 0.1 to the third divided by 6, or 3 factorial. Oops, I did 0.3. Oh, darn it. 0.1. And then I'm going to do plus 0.1 to the fifth. And then I'm going to divide it by 5 factorial. That's 5 math over to probability number 4. And it did something weird there because I hit it too fast. Let's delete that. All right, I'm good. Still probably going to give me the same thing. So I get 0.099. No, I lost it. 835. 8353333. Now what I'm going to do is actually, and that would be my approximation. And now I'm going to actually do sine 0.1 on my calculator. And I end up getting, in green, 0.099833466. And you'll notice that I have a match right up to here. And what you can do is we know that our error, because this is an alternating series, by the alternating series error bound, remember the the error is going to be less than or equal to the first unused term in the sequence. Well, my next term would have been a minus 0.1 to the 7 over 7 factorial. So that's actually going to tell me the most my error can be, and I don't have time to do that. So the assignment was to do example 4 on the next page on a blank sheet of paper and bring it in. It's videoed. You can watch that in Schoology, and that's all we did on Thursday. So the only assignment is to go watch one more video, the example 4 problem. Have a good one.